Kia ora, Year 12. In this video, I'm going to go through one of the most important integration techniques that we'll learn this year, and probably also the weirdest until you get the hang of it. So what I'm going to do in this video is show you two examples first. I'm going to teach you how to do it, and then I'm going to show you why it works. And after that, we'll do a couple more examples. So I want to start by looking at this integral here, the integral of x cos x dx. And you'll notice that in all of these examples, I've just done indefinite integrals. Okay, but once you've got the hang of it, for indefinite, it transfers easily to doing definite integrals. If you think about x cosine x, we've got a product. And that should make us a little bit worried about how we're going to go about integrating it. If you look at this and naively just try, and this is pretty, in a second, going to be pretty clear why this is a silly thing to do. If we just try that the integral of that is x sine x, let's see where that goes wrong. So suppose we start with the function x sine x here, and we differentiate it. We'll see pretty quickly that we don't get to x cos x, because we're going to have x times cosine of x, which is all good, but then we also have sine x times 1, right? So we've got this extra thing in here that is causing us trouble. And integration by parts is going to give us a way to deal with this problem. So when we do an integration by parts problem, we kind of start by looking at what we're trying to integrate and thinking of it as a product. And here that's pretty obvious. I've got this times this. We look and we ask which of those things is going to be okay when we integrate it, and which is going to get worse when we integrate it. If we integrate x, we're going to get x squared on 2. So we don't want to integrate that. Integrating cosine of x, we will get sine of x, which is, it's no better or worse. It's about the same level of messiness. So I'm going to write down here I for integrate, and I'm going to write down here L for leave the x alone. And underneath it, I'm going to write I and then D for differentiate. So this is going to be the first term, and this is going to be the second term. And none of this will be making any sense yet. Okay, so watch what we do, and then we're going to check that it works, and then I'm going to give you a proof of why it works. So we're going to integrate cosine of x, and we're going to get sine of x. So we have sine of x, and we're going to leave the x alone, right? So integrate and leave sine of x times x. Now we're going to take away the integral of this one integrated, so sine of x, times this one differentiated. I'm sure you're going, this is just bizarre. Like, why is she doing this? And that's certainly what I thought for the first probably year or so that I did this, because no one ever showed me a proof. So we're going to do the proof in this video. So we've got x sine x minus the integral of sine x dx. So just looking at what's happened, I started with this very bad integral, and now I've magically at this stage got this thing here, which is all good, and I've got an easy integral. So the next line will be x sine x. I want to end up with minus sine x, so it's going to be plus cos x, because that differentiates to negative sine x, and then I'm going to whack a plus c on the end. Now, it doesn't matter if this is a plus c or a minus c. The idea from AS in level 2 is that this is just an arbitrary constant. So we're always just going to write that as plus c. Not a big deal. Okay, now I want to have a look at whether it's worked. So we're going to start with my answer. So y equals x sine x plus cos x plus c, and we're going to differentiate it and see that we get back to x cosine of x. So in here, we've got the product rule. X times cos of x plus sine of x times 1, right? So that's that bit done. Differentiating this will give me minus sine of x, and the plus c goes to 0. So look at that, it worked, right? So somehow whatever we did meant that I got rid of the extra product rule-y stuff when I was integrating. We're going to do one more example, and then we'll do a proof and look at what on earth is going on here. So example 2 is this one here. Now you could do this integral with a technique called substitution, which we also haven't done yet, but we're going to do it with integration by parts today. So the first thing to do is to get rid of that surd sign and write it with a fractional power. Right, let's look at this and decide what are we going to integrate here and what are we going to leave. So we want to end up with something that gets differentiated. And in this case, it might not be that obvious which way to go. So I'm going to show you the way to do it here again. This thing here looks worse, but we can integrate it, right? So we can integrate that thing there. We can also integrate this very easily. Both of them in this case are going to get worse when we integrate, right? So in that first example, the x was going to get worse and the cosine was going to stay kind of around the same. Right, down here, they're both going to go up a power. But when we differentiate that x, we're going to get a very beautiful 1. So that's going to be the thing that I choose to leave in step 1 and then differentiate in step 2. Now, this is a bit of an art, right, figuring out what to integrate and what to leave, and you'll get used to it as we go. But for now, we're just going to do it and see what we get. So this equals, integrate this. Integrating this will give me 2/3 of x plus 2 to the 3/2 times, leave the x alone, right? So that's integrate and leave, minus the integral of this. So I'm integrating this, and this time I'm differentiating this. And you can see that we're getting an easier integral to work with here. So cleaning this up, we get 2x on 3 times x plus 2 to the 3/2 minus, well, let's see what's going to happen here. I'm going to have 2/3. I'm leaving a gap for an adjusting coefficient. I've increased the power by 1 to 5 on 2, and now I need to multiply by the reciprocal of 2/5, and I need plus c. So that gives me 2x on 3 times x plus 2 to the 3/2 minus 4/15 times x plus 2 to the 5/2 plus c. Right, now we're going to check that one back because that really looks quite mucky. So we're going to again say, does it work? Well, if y starts off as 2/3 of x times x plus 2 to the 3/2 minus 4/15 times x plus 2 to the 5/2 plus c, what do we get when we differentiate? Well, dy by dx is going to be found using the product rule for this one. So there's my first function, and there's my second function. So it's going to be 2/3 of x times 3/2 times x plus 2 to the 1/2 plus 2/3 times x plus 2 to the 3/2. That's that bit done. Take away 4/15 times 5/2 times x plus 2 to the 3/2, and the plus c differentiates to 0. Now I'm going to clean up a whole lot of constants. So the 3 simplify, the 2 simplify there. Nothing to do in here. And then in here, 4/2 is 2, and 5/15 is 3. So cleaning all that up gives me x times x plus 2 to the 1/2 plus 2/3 times x plus 2 to the 3/2 minus 2/3 times x plus 2 to the 3/2. So again, you can see that what we've got is we've got what we wanted, and then we've got this extra bit, right, extra bit here that we then took away. So we end up with exactly what we were after, right? We wanted to figure out if we differentiated my answer, did we indeed end up with the thing we were trying to integrate? And we did. Okay, so that's 2 examples, and that's already used up 9 minutes. What I'm going to do now is I'm going to show you the proof of why it works. And it's all to do with the product rule. Okay, so we're starting off with a basic product rule setup. So the derivative of uv with respect to x is equal to u times dv by dx plus v times du by dx. Now we can integrate both sides. So the integral of this has to equal the integral of this side. And we know, I guess at this level, we just know intuitively that we can split that into these two integrals, right? We do that all the time. When we're integrating 4x plus 3 dx, we're really splitting that up into two integrals. Okay, so I think the thing that is you have to get your brain around here is that when we differentiate and integrate, we're doing inverse operations. So the integral of the derivative gets me back to what I started with, which is uv. So this thing here, which looks awful, is simply uv, right? But we can't say the same about these two things here. So we've got uv is equal to u times dv by dx plus v times du by dx. I'm going to rearrange it now, and I'm going to make this the subject. Okay, so we get u dv by dx is equal to uv minus this. And hopefully you're starting to see that this has got the pattern that we had up the top, right? So here we've got no integral sign, and we've got something, and then we've got a takeaway sign, and we've got an integral sign. So let's see how that fits in with the pattern of what we just did. Well, we had x times cos of x dx. And in this one, this u is going to sit here the same in the first bit, and then it's going to get differentiated in here. So in here we chose u was equal to x, and in here dv by dx was cos of x. And so in here we don't want dv by dx, we want v, right? And so v is what we get when we integrate this, which is sine of x. Now all of the plus c's just end up washing out in here at the end, so don't worry about that too much, okay? But I'll put that in there because to me it feels terrible to write an indefinite integral without a constant at the end. Okay, but that's what's going on. Now that's 12.5 minutes. I'll just show you what we chose for u and v in the next one. So the u that we're choosing is the thing that we're leaving and then differentiating. So in this case, again, we chose u as x, and we chose dv by dx to be x plus 2 to the 1/2. So that gave us v, which was its integral, was 2/3 x plus 2 to the 3/2. Okay, so that integral is what's going into both there and into there. Okay, and so u was x and du by dx, oh, why is it doing that? Du by dx was equal to 1. Okay, this video is long enough already, so that's 13.5 minutes. I'm going to stop here and go off to a meeting. I promise later on today I will YouTube examples 3 and 4, but you could try them first. Now, example 3 is actually really easy. It's probably easier than the first two we've done. Example 4 is harder, and you'll have to think about doing integration by parts twice over. But once you get the hang of it, this is a really fantastic technique, and we'll be spending quite a bit of time practicing it between now and October. Okay, thanks for watching, guys, and have a good day.